Hello, my name's Jeff Messier. I'm a professor in electrical and software engineering in the Schulich School of Engineering. And in this lecture, we're going to continue to learn a bit more about assembly language programming. And I'm basically just going to talk about a series of essentially mathematical and logical calculations that we can implement in assembly language and that often come in handy. The first family of operations are logical operations. And if you look in the AVR instruction manual, you'll see that there are a whole range of the ones that you would expect. There's bitwise AND operations, OR, XOR, NOR. And bitwise logical operations are most useful when manipulating individual bits within a byte. So, and this is particularly handy for AVR programming because often we might be dealing with a special function register where we have to, set just maybe the third bit in order to configure some I/O or peripheral functionality. Okay, so if we take a look at our development environment, in this assembly language program, I've just got a text segment, so we're not going to be using data memory to sort of demonstrate the functionality of the operations we're going to be talking about. And so what I want to do is just give you a little bit of a demo regarding some of the common things that you use logical operations for. So let's start out by copying in a value into register 16, just so we've got something to work with. And I'll make a little section here called logical operations. So the first thing that I want to do is load in the number 1 into register 17. And I want to use register 17 to set the least significant bit of register 16 to 1. And the way that I'm going to do that is by using the OR operation. So I'm just going to go OR register 16 with register 17. And this is going to implement register 16 is equal to register 16 bitwise OR with register 17. And if we save that and compile, I'll just set a breakpoint on our first command here, start the debugger, and we're working, I've still got the data memory screen open. We're not using data memory for this particular lecture. Instead, we want to look at register values. So I'm going to create a new watch for register 16. Oops. And a new watch for register 17. Click OK. And then using the step into button, I go ahead. So register 16 has a value of AA now. Register 17 has a value of 1. And if we step over the OR, we can see that register 16 has changed from AA to AB. So the number 10 in the least significant byte of register 16 has changed from 10 to 11. And that's because our OR operation has set the least significant bit to 1. And again, this is handy for particularly when working with the AVR, when you look at special function registers for configuring things like the analog to digital converter or digital I/O pins. Sometimes we want to toggle just a particular bit within a register, and these bitwise logical operators are handy for that. So I'm going to stop the debugger. And the OR operation is useful for setting a bit. The AND operation is useful for clearing a bit. So to demonstrate that, I'm going to load into register 17 the value of 7F. And so if we wrote this out in binary, R17 would be equal to 0B 0, 1, 1, 1, 1, 1, 1, 1. So register 17 is equal to all ones except for the most significant bit. And I'm going to AND register 16 with register 17. Save, I'll compile. This time I'm going to move our breakpoint down. Run. Okay, so if we look, register 16 contains AB, right? Because we earlier on with our OR command set the least significant bit to 1. We're now going to step over the LDI command. So now the contents of register 17 is 7F. And if we step one more, if we execute our AND operation, register 16 changes from, the most significant byte changes from 10 until 2. And that's because we zero out the most significant bit, which was equal to 1. Now, again, the way that you need to work through these lectures is implement this exact code. So I'm, again, on purpose, I'm not handing out source code that you can just kind of scan through. I want you to literally be typing this stuff in, thinking about it as you type, stepping through things in the debugger, just like I'm doing right now in the lecture. If these bitwise operations don't make sense to you, do them by hand. So write out these values on paper in binary form and convince yourself that we're properly setting and clearing the bits as I'm representing here. So the next group of operators I want to talk about are the shifting operators. And we are able to take our register values and shift the bits either one position to the left or one position to the right. And what I mean by that is, for example, our first command is logical shift left. It takes the format of the command is LSL, and then you give it the name of a register. And it shifts the values stored in RD to the left by one position. And the least significant bit is set to 0. So for example, if we had LDI R17 0xFF, LSL R17, R17 would then equal 0xFE, because our 8 bits, when shifted to the left one position, everything sort of goes to the left. So we have 1, 1, 1, 1, 1, 1, 1. And then our new bit, so we had no bit here. So the new bit that gets shifted in is equal to 0. Logical shift right is the same thing, except it moves things to the right. And it shifts the value right by 1, and then the most significant bit is set to 0. So there's two reasons why we like the shift operations. One is to just, again, to sort of manipulate bit values. You know, if we've got some register, if we've got some bit in our register that we want to shift down so it's the most or least significant bit, we can use these shifting operations. Shifting, however, is also equivalent to a mathematical operation. Shifting left is equivalent to multiplying a signed or unsigned value by 2. Shifting right is equivalent to dividing an unsigned value by 2. Now, the reason why, and I just want to make this point. So the LSL operator works for signed, signed or unsigned values. So if you shift a signed or an unsigned number to the left one position, it's equivalent to multiplying that number by 2. And convince yourself of this if you're not following that. So just do a few examples with some 4-bit numbers and convince yourself that shifting is equivalent to multiplying. Shifting right is equivalent to dividing by 2, but logical shift right only works for unsigned values because it doesn't preserve our sign bit. So the most significant bit that gets shifted in is always set to 0. That means if we are working with a negative number, for example, our most significant bit is our sign bit, and that sign bit is set to 1. If we shift, then we lose that sign bit. So the logical shift right operator cannot be used with signed values. So back to our code demo here. And I'll make a shifting left and right section. I'll shut down our debugger from our previous thing. I'm going to get rid of our breakpoint. And to just sort of illustrate how this works, I'm going to load in the number 4 into register 16. And I'm going to start by shifting register 16 to the left 1 place. And this is shift left once. And this is equivalent to multiplying by 2. So just to prove that, I'll set our breakpoint, save, compile. I'll run our code here. And so we stopped at loading 4 into register 16. I'll step ahead 1. We can see that we've got the number 4 in register 16. I'm going to shift those bits to the left by 1 position. And we can see that 4 changes to 8. So sure enough, it is equivalent to multiplying by 2. Now I'm going to do logical shift right, R16. And I'm going to do 2 logical shift right calculations. And if you shift right twice, it's equivalent to dividing not by 2, but by 4. Shift right twice. Divide by 4, and run our code again here. So there's 8 in register 16 after we multiply by 2. And then let's shift right once. We're back down to 4. Let's shift right again. And now we're down to 2, right? So 8 divided by 4 is 2. And remember, shifting right, if you want to use it for the purposes of division, can only be used with unsigned numbers because this particular shift operation does not preserve the sign bit. So addition is also another important thing for computers to be able to do. As it turns out, there are a few variations of the addition operation in the AVR instruction set. Here are 3 examples. The first command, add without carry, is just the add command. And this is just regular old addition. So you type in add, you give it 2 registers, and this is equivalent to RD is equal to RD plus RR. And we're familiar with this command. We talked about it a lot when we were designing our microarchitecture. A second variation on command is add with carry. It's exactly the same thing as the regular add, except the carry bit from the previous operation is included in the addition. This is useful if we are performing an addition that's on a word that is larger than just 8 bits, right? So if we have, let's say, we want to add 2 16-bit numbers together, or 32-bit numbers, 64-bit numbers, we would add the first byte, and then we would need to take that carry from the most significant bit of the first byte addition and then bring it into the addition of the next most significant byte. And so add with carry is used for multi-byte words. And there's also an add immediate operation. So this is an add immediate operation where you can just put the number that you want to add onto, like, right on, embedded within the assembly language instruction. And this is add immediate to word. And so you can take a number and add it to 16 bits. This only works with the X, Y, or Z register pairs, and it's used basically to increment addresses. So if you've got a data memory address in your X, Y, or Z register pair, you can add an immediate to it, so an offset to it, and it automatically performs the 16-bit addition. And so it treats the X, Y, or Z register pair as a 16-bit number. Okay, so I'll just do a quick demo of the add operation here. This is not, terribly earth-shattering. So I'm going to load a number into R16. I'll load 15 into register 16. I'm going to load the number 1 into register 17. And I'm just going to add these two things together, the two registers together. I'll bump down our breakpoint here. All right, so I'll hop through these load immediate commands. As you can see, we've got 15 loaded into register 16, 1 loaded into register 17, and if we execute the addition, register 16 changes to contain the number 16. And finally, subtraction. So just a couple of the subtraction commands summarized here. The sub command is the mirror to the add command, basically. So sub RD/RR implements RD is equal to RD minus RR, as you would expect. Unlike addition, there is also a subtract immediate command that works just with regular registers, not with like the X, Y, and Z register pair. And so you can just specify an 8-bit value and just go subtract immediate, give a register, give an 8-bit value, and this particular command only works with registers 16 through 31. So I think it was designed with an eye towards the XYZ register pair, but it works with all registers 16 and higher. All right, just doing some subtraction here. So LDI R16, let's put in the number 1 into register 16. And let's try out this subtract immediate command. So I'm going to take register 16 and I'm going to subtract 4 from it. So the result is going to be -3. So let's make sure that it handles the whole 2's complement thing properly. That's a broken breakpoint because I didn't stop the debugger. All right, so let's rebuild and compile now. And run. All right, so we've got number 1 in register 16, and let's subtract 4 from it. And sure enough, we can see we've now got a bunch of 1s in register 16. And if you double check, you will see that this is the correct 2's complement representation of -3. Okay, finally, multiplication. So there are multiply commands for signed and unsigned numbers. And for both of these commands, you just give the 2 registers that you want to multiply together. Unlike addition and subtraction, the result is not copied back into the registers that you're operating with. Instead, they're put into R0 and R1. So the low byte of your multiply operation is put into register 0 always, and the high byte, or the most significant byte of your multiplication, is put into register 1 always. And I'm not going to bother demoing them, but just be aware that fractional multiplication operations exist as well, and those are meant to be used with fixed point numbers. All right, just to demo the multiplication operation now, I'm going to load a couple of values into register 16 and register 17. You'll have noticed in all of my lectures I kind of obsessively use hex numbers, but you don't have to. You can just give regular base 10 numbers if you want. And so I'm going to put the number 51 into register 16 and the number 5 into register 17. And so if you multiply those two together, you get 255, or FF hex. And I'm then just going to do the multiply command, register 16 with register 17. Oops, or 17. And I'm going to add a couple of watches so we can look at register 0 and register 1. All right, so I'll set a breakpoint. Save. Compile and run. Okay, so we've got hex 33 and register 16, hex 5 and register 17. And when I run the multiply operation, we can see, sure enough, that, like I said, 51 times 5 is 255. So that can be contained entirely in the least significant byte. So it does generate a 16-bit result. But because the upper byte is 0, register 1 is equal to 0, and register 0 has the result 255.